Okay, so since most groups are working on the third problem, I'm going to talk my way through it. If you are happily working on this problem and you don't want to pay attention, you are welcome to ignore me. Okay, so they say the x-coordinate of an electron is measured with an uncertainty of 0.2 millimeters, so that's our delta x. They want to know what the x component of the electron's velocity is if the minimum percent uncertainty, so percent uncertainty in velocity is 1%. So that took me a while to figure out how in the heck I'm supposed to get velocity if I'm given percent uncertainty in velocity, because the first thing I wanted to do is I wanted to say this must be equal to my delta V. But it doesn't have units of meters per second, so it can't be delta V. No, the percent uncertainty in velocity is actually my delta velocity over my velocity. And that's my percent uncertainty in velocity. So given that, I can solve for my velocity. But right now, I really just need that delta V, since I have a delta x. So that's what I'm going to do for delta V. Now, where's delta V in this equation?
It should be delta V, isn't it?
Yeah, this is my equation. There's no delta V in it.
Well, no, but I mean, isn't that if momentum is mass times velocity? Should be delta V delta M?
Yeah, so you put in the delta of m times v. In this problem, let's assume we're not moving at relativistic speeds and the mass doesn't change. And the only thing that's actually changing that would have some sort of uncertainty in your measurement would be your velocity. So I pulled the mass out. And then my equation becomes mass times the change in x times the change in v. And then I don't ever remember the constant h bar, but for some reason I remember the constant h. So I just made that h over 4 pi. That's one less constant I had to look up in the back of the book. So, okay, so they want us to find v. It's over here in this guy. So I'm going to put that in. So I have m, delta x, and then for delta v I'm putting in v times 0.01. And you know, I don't want to overthink this, but whenever you've got problems that say stuff like if the minimum percent uncertainty is blah, and then find the exact value velocity, so they're doing something with this less than or equal sign, and then the minimization of it basically is forcing it into an equal sign. Don't overthink it, because you'll talk yourself into circles. So when you're taking a minimum or you're taking a maximum, then you're looking at a limit. And so then that gets rid of your less than or equal signs or greater than equal signs. Okay, so our goal here is to get out our V. So now it's just algebra to get that term by itself. So what I ended up with was an equation like h over 4 pi m delta x times 0.01. And then you can plug in for the mass of an electron. And I got the velocity was, I'll let you guys tell me what you guys got. 28.939, 28.595. It probably depends on what value of h you use. So I'll just leave it that, 1 sig fig. Mass of a proton, what'd you guys get for the velocity of for the mass being a proton?
0.158. Or I guess we could probably do millimeters.
Yep, so you can write it as 0.0158 meters per second. You could write that as 15.8 millimeters per second. So once you've got this equation in your calculator, then you can repeat the equation and change the mass to the mass of the proton. So part B doesn't take very long because you've done the bulk of the work already to get to the answer to part A. So were there questions on that problem still that lingered after that explanation?
I just didn't know what to do with that percent uncertainty, weird stuff.
Oh yeah, no, I didn't either for a while, and I think this is one of those where if you've seen the problem, you know what to do, but if you haven't seen the problem, then that can be your big hang up. And you end up either using it incorrectly, which I almost did, or just not really knowing where to go. So that's part of the reason why I wanted to show this one to you, so that if you see it again, you kind of know what to do with it. Because that's kind of a weird thing we haven't really done before, showing percent uncertainty. So, okay, well, moving right along, we're going to get back to the lecture now. So de Broglie takes as a hypothesis that particles behave like waves. Electrons, this is a very easy jump to make because electrons have such little mass. And so he says, let's assume that electrons are actually acting like waves in an atom. And the reason they can only exist at specific shells around an atom is because in order for a wave to line up with itself as it's creating a sine function, if you wrap that sine around into a circle, you don't want that sine to destructively interfere with itself, then it can only exist at certain circumferences for that wave to actually align and become a constructive path instead of destructive interference. So this is sort of like circular standing waves. That's one way to think of them. So if your shell is the second shell, like you've got your ground state energy, which is the closest shell to your atom. If you're at n equals 2, that's your second shell. This is what he proposed the configuration would be. That's where you've basically got 2 wavelengths appearing. And then for your third shell, n equals 3, you'll notice that there are 3 wavelengths for that electron. And n equals 4 wavelengths. So that's a really nice formalism. And it was really, it came along during the time when we were constructing atomic models, which I'll get to a little later, and you'll spend a lot of time on your online activity exploring. But this was pretty groundbreaking in its usage here for the atom. So another way to describe waves, and this one you'll learn about on your weekly online activity, is called the Schrödinger model. Instead of a wave where you actually see a particle moving along a wave-like path, or you see standing waves on a string except in a circular shape, how would you expect a wave to actually look when your electron is really, really small? You don't have a string, you've got this particle that's moving around so quickly. What you end up having is this cloud, an electron cloud. And these are actually photographs, real photographs. And this is the hydrogen atom in different excited states. So the electron has different energies. There's just one electron in the hydrogen atoms. This is one electron creating this pattern. These are electron clouds. And another way to think of them is a probability distribution. So the points that are white have the highest probability of the electron existing in those locations. As the colors go from yellow to red to blue, the probability drops off. But there is always a measurable probability the electron could exist at the far edges of the universe. That electron can be anywhere, but it has the highest probability of being within that electron cloud. Heisenberg uncertainty principle says we can't actually know where exactly it is in the cloud. So this sort of helps us, I guess, come to grips with the reality of the world. The electron isn't really pin downable. So having a probability distribution makes a whole lot more sense than our old model, which said you've got this circular orbit and a very defined particle orbiting at a very specific location. In reality, you can't pin down exactly where that electron is. So some of the shapes you get with different energies, this is like de Broglie's concept of the second energy level, n equals 2, where you get 2 wavelengths. This is the actual image of an electron cloud for n equals 2. And then these other numbers are quantum numbers. So the first one is n, and so that's your shell number. And then these are sort of sub-energies. So the second one is related to the angular momentum of that electron. And you can change its angular momentum, but keep it at the same shell level, and that'll change the configuration of the cloud. So it's still at n equals 2, but now you've got an angular momentum of either 0 or 1, and you get a completely different shape. And then here's one of the configurations when it's at the n equals 3 shell. So remember, this is a 3D shape that we're looking at a cross-section of. So here, you're seeing like a ball and then an outer ball. So like an inner ball and an outer ball. And this one, you're seeing 2 balls connected at a small singularity, basically, at that point. Nothing exists. No electron would exist right between them, but that's actually where the nucleus is. This one, what do you suppose the shape is? You figure out what the shape would be, or might be? What's that?
Like a clover?
Like a clover? It kind of looks like a clover.
It's like a donut with things sticking out of the middle.
A donut's getting closer, so it's like this shape where you've got these 2 sort of, it's almost like an old hourglass shape here and here, and then it's surrounded by a donut. Yeah, so that's what that cross section is actually doing, which is strange. Here's a whole bunch more of them. So you can kind of see this is. Yeah. Yeah. So we get more and more complex patterns as the energy of the electron increases, and I don't know why, but this always reminds me of standing waves on a platform. So I don't know if you guys have ever seen this YouTube video. So this is sand on a platform, and there's a speaker underneath it, and the speaker is being vibrated at frequencies, and then they're just turning up. It's a constant frequency. They're just changing the frequency, and the pattern in the sand gets more and more complex as the frequency increases. So I don't know. This is very reminiscent to me of the electron clouds. And it sort of, there are standing waves where it's crystal clear, and then when you're between a frequency that's not one of the harmonics, it sort of creates chaos. So it can't create a standing wave unless it's at one of the harmonic frequencies.
Ooh, that's cool. Okay.
And so that's going to be very similar to the electron. It doesn't exist at one of the intermediate energy levels because you just can't create a standing wave.
10 kilohertz. That is awesome. Now we're at tinnitus level.
And some people in here might not be able to hear it At some point, you're going to get to a point where you can't hear the sound anymore because it's above your level of hearing.
It's about to get there. Until it vibrates at somebody's natural frequency and they explode.
Is that the brown note?
That is awesome.
That's ridiculous.
Thank you.
And then just slowly changing that with me. Some of them are quick changes, some of them are slow.
There's calling it out for us. Oh, wait, there it is again. Oh.
So anyway, you guys get the idea. I think it's really fascinating that de Broglie proposes that electron waves are like standing waves, and it looks very much like the standing waves you get in sand. And so I think that really helps my understanding of why that electron can't exist at intermediate energy levels, because as we see with waves on a string, there's only certain frequencies that are allowable. You just get chaos in the in-between.
So I'm curious, what like amplitude in terms of like decibels would you have to have that loudspeaker going at for the same
To get it to work? I don't know. I've wanted to just go to Goodwill and buy an old speaker and make one. It wouldn't be hard to make. It's just a matter of time. But I think this classroom needs something like that to play with.
But you have to get the
I just pass around earplugs. Yeah, earplugs.
Double.
So
Depending on how
So we saw in those pictures that we had 3 numbers describing the shapes, and so just to tell you the names of them, n is called the principal quantum number, and it can be any integer 1 to infinity. L is the second number, and it's called the orbital quantum number, and you can have values, any value that's less than n minus 1. So if you're at energy level 4, so if your n equals 4, then all the possible n's or L values that are less than or equal to 3 are going to be energy levels. So for n equals 4, L can be 0, 1, 2, and 3. And then the orbital magnetic quantum number is associated with the magnetic moment, and those numbers can be 0 all the way up to L. So 0 plus or minus 1, plus or minus 2, plus or minus 3. So you get every combination in here. So we'd have 4, 0, 0, 4, what's next? 4, 1, 0, 4, 1, 1, 4, 1, negative 1. So on and so forth. 4, 2, 0, 4, 2, 1, 4, 2, negative 1, 4, 2, 2, 4, 2, negative 2, so on and so forth. So there's many more that you could keep writing just for n equals 4. These are all the possible energies that electron could form itself into with these quantum numbers.
Just like the, like in chemistry, they have like the S, P, and D.
Yes, yeah. It's just like chemistry. Everything learned in chemistry.
Okay.
Same in physics. Yeah.
Ish.
Ish? Well, sometimes they use different variables.
It's the chemist-physicist fight.
Yeah. But in reality, it's the same.
Well, yeah.
We can fight about variables, but it's the same. Okay, so the atomic models. In 1887, J.J. Thomson discovered the electron, and they already knew that atoms had some positive properties, and then they discovered they had negative properties as well. And so he said, well, it must be like plum pudding. There's this positive goop and negative particles floating in that goop. So that was 1887, and that worked for a while, but the more experiments people did, the more they realized that there would be some interaction between the positive and negative charge in there. So you could never have positive charge goop surrounding negative charges because it just wouldn't coexist like that. So in 1911, we get the Rutherford model, which says there's got to be a positive nucleus separate from those negative electrons. And the most logical explanation is to look up at the sky. It's like orbiting planets. So they use classical mechanics to describe this, where you've got an electron orbiting the nucleus using classical mechanics, equations and whatnot, except the intermediary force was electrostatic force instead of gravitational force. That failed miserably almost immediately when they started testing it, and they figured that their predictions said that as the electron orbits, it's going to lose energy. And as it loses energy, it's going to spiral towards the nucleus, and it would explode. So they call this theory catastrophic. Because every atom, if this was true, every atom in the universe would just explode, which doesn't happen, so they ditched the theory. And in 1913, Niels Bohr came along. He's a student of Rutherford, and he said, the orbits are a good one, but they have a specific distance from the nucleus, and they can only exist at specific orbits. So we've already studied the Bohr model. So this makes a lot of sense if you've taken chemistry. The more energy an electron is, it'll jump to a higher orbit, but it can't exist at any intermediary distance. It only can exist at very specific distances. If it loses energy, it'll emit a photon and jump down to a lower level. In order for it to gain energy, it's absorbed some kind of it's absorbed a photon, and that's what allows it to jump to a higher level. So if you're talking about an electron that's dropped from a higher energy level to a lower energy level, here's a little diagram of that happening. So this is the initial energy, this is the final energy. It's losing a photon in the process. The photon has a very specific energy equal to HF. That's what Einstein said it was. That's exactly the size of the jump that the electron makes. It loses that amount of energy conservation here. So the change in energy from its initial energy to its final energy is equal to HF. You can write F as C over lambda, since the frequency in this case is the frequency of that photon that's emitted. So this would be the energy gain or loss of an electron, that if it gains energy, then it absorbed a photon, and if it loses energy, then it emits a photon. It's a photon. There we go. All right, so here's a picture that kind of describes the energy jumps in some terms that chemistry folks have probably heard before. So any time that an electron jumps from a higher energy level back to n equals 1, the ground state, they call that jump part of the Lyman series. Anyone heard of that? This is all for the hydrogen atom, okay? The Lyman series, all the photons that are emitted when these jumps occur fall in the ultraviolet range. So you probably haven't heard of the Lyman series. Anyone heard of the Balmer series? Maybe nobody's heard of this, okay. Well, the Balmer series is the one you might have heard of, because these jumps are what emit photons in the visible range. So these are jumps, anything above n equals 2 down to n equals 2 will emit photons in the visible range. And there's some other ones, the Paschen series, bracket series. Anyway, so the Paschen series is anything that jumps down to n equals 3. So those three are ones that you should make note of the names. So Lyman is anything that jumps down to n equals 1. Balmer is anything that jumps down to n equals 2. And Paschen is anything that jumps down to n equals 3. This is the same picture, they've just taken it and linearized it. So, some things you can notice about this graph is for the hydrogen atom, the lowest energy, the ground state energy, is negative 13.6 eV. That's a constant that's true for every hydrogen atom. If you have some other atom, it's going to have a different ground state energy. And we've talked before about this electron well. So the electron with the photoelectric effect was sitting down here at the ground state, and it needed to jump out of the well to escape its atom. So for hydrogen, yeah, for that well was exactly 13.6 EV deep. So the work function for hydrogen would be 13.6 EV. That's how much energy that electron needs to escape its atom completely. Okay, so we've also talked previously about the emission spectrum. And we had the pictures of the emission spectrum for hydrogen and helium and sodium, and neon was another popular one. And we used our spectrometers back there, those silly plastic things, and you could see emission lines for the lights. So every time an electron jumps down an energy level, it emits a photon of a very specific wavelength based on how much energy it lost. So in the visible range, those are the lines that we see on an emission spectrum. Those are the visible lines that we see. So for hydrogen, we see 1, 2, 3, 4, 5 characteristic emission lines in the visible spectrum. So as I said before, the visible spectrum is related to the Balmer series. So those 5 lines that you're seeing are from the Balmer series. We know exactly, we can, based on the wavelengths of light that we see, we can calculate exactly how much energy that electron jumped in order to produce that wavelength of light. So how they're getting these pictures, if you were to just send white light, or if you had sunlight and you sent it through a slit and then through diffraction grating, this is just like we did with our spectrometers, you'd get a complete spectrum that you'd be able to see. But when you send some sort of gas through that diffraction grating, like when we looked at our overhead lights, then you saw only specific emission lines. And if you want to know, you make these vacuum tubes with a very pure gas, then you'll see the emission lines for just that gas. So someday I'll be able to afford this. You can buy these little physics kits, and you can get these little vacuum tubes with just hydrogen inside or just helium inside, and you just plug it into a little power supply. It warms up that light, and then you can create these emission lines to demonstrate to your students. So that's my pie in the sky grant request. I think I need about $1,000 to buy the kit. But these are the images you'd get for doing that. So we've seen these before. Okay, so questions about the hydrogen atom, the Bohr model, how the Bohr model represents the hydrogen atom so far? Okay, so I think 39.5 is just simply taking some of these wavelengths, these characteristic emission lines that you get for hydrogen, and plugging it into this equation and calculating the energy jump. So it's not a super complicated problem, so I didn't want to do that one in class. All right, so I showed on the board, if you had for n equals 4, for example, all the different possible energy levels that you would get at n equals 4. So this is kind of written in a tabular format for that. And so when the chemistry folks were saying the S shells, the P shells, that's showing up here. Those aren't the shells. That's I don't remember what the S and P's were called. Energy levels, that they call it. What they called the shells was for n equals 1, that's the K shell. For n equals 2, that's the L shell. I don't know why they use KL. Why don't they just call it n equals 1? I was calling it n equals 1. So, but anyway, these are more terminology that you may